In thermodynamics, there exist two seemingly incompatible concepts. First, consider the ergodicity principle, which boils down to, each stochastic system will eventually visit its initial state an infinite number of times. Second, there exists the concept of entropy. In any stochastic system, entropy tends to increase, until it stabilizes when the system arrives in equilibrium. We call this process heat death. This poses an immediate question. If the closed system eventually returns to its initial state, how can entropy tend to go down? The entropy of a point in the future is precisely the same as it was when it started, so wouldn't one expect the entropy to remain constant? To get a bit more feeling with both of these concepts, let us look at a toy model. Imagine we have a pair of dice. Both are placed on the table with the one-eyed side upward. Each second, we select the die with the lowest number of eyes, and reroll that die. If both numbers are equal, we reroll both of them. For example, currently, a 4 and a 2 are facing upwards. 2 is smaller than 4, so we reroll the white die. It ends up at a 5. 4 is less than 5, so we roll the black die this time. It ends up on a 3. 3 is still less than 5, so we throw the black die again. We roll a 5, so now we roll both dice. This process will go on forever. If you want a process closer to thermodynamics, instead of imagining them like dice, you can think of them as an artificial atom with 2 electrons. Both electrons have opposite spin and have 6 orbitals they can find themselves in. It is impossible to construct an interaction equivalent to our dice without adding energy to the system, but many complex systems have similar properties. So just roll with it. Calculating the entropy of this system is quite doable, but to keep it simple, we will instead consider the largest die of each atom, and calculate the average over all atoms. We could make an argument about whether or not this is a good proxy variable for entropy. But in the end, the only property we are interested in is the fact that it tends to increase. Hence, all we need to do is check if the entropy increases in practice. As you can see in this diagram, the entropy increases fast, and when the system reaches equilibrium, the entropy remains constant. This is exactly what we need. Our definition of entropy is thus a good proxy variable. Let us have a look at the ergodic principle. It is easy to calculate how long it takes for our system to get back into its original state. Each atom finds itself in its original state 1/215th of the time. Using this fact, we can calculate that a mole of atoms has a chance to find itself in its original state of 1 in 10 to the power 10 to the power 24. This is a number that is so big that it is incomprehensible. Although we are certain that it will happen at one point, the time it takes is unimaginably large. We have built a system where heat death is reached almost immediately. Considering this, it is easy to see how this isn't at odds with the entropy principle. Entropy makes a statement about the general trend, while ergodicity makes a statement about very rare outliers. So in general, both statements are not at odds with each other.